Now the question is, how do we get from absorption, that is, we are measuring a number of photons arrive in a detector, that we can measure. We can measure the number of photons that arrive in the tissue, so we can measure what goes in and what comes out. But how do we reconstruct an image based on that? And this is what we are going to discuss now. So let's say we have a tissue here with 3 different layers. A position y0 of the first layer, and each layer will say has a thickness of delta y. Doesn't matter what the thickness is. Centimeter, millimeter, micrometers, doesn't matter. We'll just say this is a certain thickness, and we have 3 different tissues here. We have at the position y, at a certain position y, we have an intensity or a number of photons I of y that impact this tissue layer here. And we'll assume that they are the same for the entire thickness, that there's a certain number of photons that comes in here. So we have a certain beam intensity, there's a number of photons at a given position y0. And so we can now calculate what is the intensity at y0 plus delta y. And this intensity is obviously given by the same equation we have discussed earlier and last week. The intensity at this position here is given by the intensity of the photons at this position, that's the incoming photon beam, times e to the minus mu, the linear attenuation coefficient, at this position, times delta y. Here we're assuming that across delta y, the linear attenuation coefficient does not change. That's a fair assumption. We can always choose delta y sufficiently small that this condition is fulfilled. Now I'm interested in calculating the intensity at this position here. We'll do that. We'll apply this equation here recursively to arrive at this expression. This is what we are going to do now. So the intensity at y0 plus 2 delta y is given by the intensity at y0 plus delta y. That's the intensity of the photons arrive at this layer here, times e to the minus mu at this position. So that's y0 plus delta y times the thickness delta y here. So that is just the same thing for this layer. We have the incoming intensity, corresponds to this one. We have the absorption, the reduction here, corresponds to this one. Notice here that we're taking the linear attenuation coefficient of this layer now, obviously. So we can now substitute this equation into this equation. That's what we are doing here. So we have done this here. Now we have this expression here. And so we will write here that the position, the intensity at this interface here is given by the intensity of the photons at this layer here times this expression here. So this is just taking these two terms and they're being summed here, up here. Now, can you see what kind of expression this leads us to? Let's say we will let delta y go to 0. And instead of making y0 plus 2 delta y, we are going to go for a summation over many delta y's. So what are we getting? Instead of a summation here, we have a summation over 2 delta y's. We're going to sum from the source to the detector of the linear attenuation coefficient and along y. I'll put in here the variable y prime, dy prime. It's minus this. This is what this sum here is. So the detected intensity is equals to the impacting intensity here times this integral here, e to the minus this integral here. That gives us the detected intensity. Now let's consider a two-dimensional object. Obviously we're not interested in a one-dimensional image, we're interested in a two-dimensional object. So we have the same object here, we have y0. We'll call this dimension again y. And we'll call this dimension here x. So the intensity observed at the position x, at a certain position x here, is now given by the intensity impacting. Well, here we've assumed that all the photons have the same intensity. They don't depend on x. So that's a normalization here. And then it's e to the minus this integral again. It's the same integral, but now we've introduced the variable x here to indicate that we also could have a variability along x. Now what does this function here mean? So we will now introduce a mathematical transform, that's the Radon transform, and the Radon transform is defined as Radon transform g of x of this function mu is given by the integral from infinity to minus infinity of mu of x y prime dy prime, so along one of those variables. That is the Radon transform. Now, unlike the Fourier transform, which has many useful mathematical properties, there are not that many easy mathematical properties for the Radon transform. But I will make the case here that the Radon transform, to know it and to recognize it in the image generation process, is nonetheless useful because we can deduce some consequences from it. So what is a Radon transform of a point-like homogeneous object? So here's my object. We'll look at the Radon transform here. This basically means we're integrating. We have only intensity at where the object is. We're getting this intensity here. If we take a rectangular object, then the Radon transform means simply we are integrating along this direction here. So that's this integral here. We're getting more intensity because it's thicker, and only along x, where there is dimension of the object. So a Radon transform is essentially a projection of the object, a summed projection of the object onto one of our axes here on the x-axis. Let's look at the Radon transform of a circular object. Here's a circular object. The Radon object transform is here. This is the integral as we have seen, and it's actually a projection of the object onto an axis. And the question is, if we take a two-dimensional object, does each pixel in that object, does each picture element, each tiny little element of the image, have a unique representation as we generate the data set? And we're going to look here at the detector. Here is a detector. Here's our object. It's got 3 holes in it. Here's the detector, and we're going to move this detector around the object. And this is what we have seen in the first video of this week's lectures. We have seen that there's something rotating inside the scanner, and this is the detector that's being rotated around the subject. This rotation, the question now is, if we do this rotation and we record for each angle a different Radon transform, that is a different projection, are we generating information that allows us to uniquely identify each pixel in the image? If we can say yes to that question, then we can reconstruct an image. And so what we are looking at here now is the angle phi, which is the angle of the detector plate here, with respect to its rotation. So we are going to rotate it, that is, we're going to change phi. This is on this axis here. And we are going to look at our 3 holes here. For convenience, I have color-coded them with different colors. The small hole is the red one, the medium hole is the blue one, and the big hole is the green one. And we are going to look what happens as we move the projection around. We start in this projection here. The green and the blue are very close on top of each other, so they are, in this projection, they are very close to each other when they are being projected, whereas the red one is fairly to the side. And so, as I rotate the plate around, this is my object as stationary. As we rotate around, and for each angle we write down the projection, we see that the position of the holes changes. So this is depending on their position. Here we obviously have an angle phi where the green is at the edge. This would be this angle here, and the blue is almost on the other side. How far away they are from the center depends on about which point we rotate, and this defines the extent, the lateralization of our object. This object is pretty much in the middle when we have this orientation, so at this point it should be around here. So let's verify that. As we are at the extreme cases for blue and yellow, red is just in the middle. So as we are doing a rotation of 0 to 180 degrees, we are seeing that the objects move in a sinusoidal pattern. And we can actually verify, if we take just a pointwise object, that the trajectory of our point, any of these 3 points, we can write in this form. It's given by a r, that's the maximum amplitude, times sine phi plus phi 0. Phi 0 is an offset that's characteristic for each of the points. And now you can think about it, that each point in my image is represented by a max different r. If they have the same r, then they will be differentiated by at which angle they have the maximum, that is where sine becomes maximally. That depends on when we are perpendicular to the position of that voxel. So this voxel has a maximum if the projection is here. The red one has a maximum here, pretty much at this orientation. So the conclusion here is that each point in space is uniquely represented by the amplitude and the phase phi0 of a sinusoidal trajectory in this plot here, and this plot is called a sinogram. So nomen est omen, it is a sinusoidal function, so this depiction here is called a sinogram. So a pixel in position x and y can be represented by a unique coordinate in r and phi 0. So the good news is we have independence of each pixel in the image. They are uniquely represented. And so the question is, what if we did a simple matrix inversion? Let's take an object that we have decomposed into a 2x2 matrix. It's not very meaningful practically, but we can assume that we can do that. And so we have 4 linear attenuation coefficients to consider. We have 4 intensities. We have measured 4 projections, 2 here, 2 here. And so with these 4 measurements, since we have 4 linear iterations to consider, we can calculate the intensity I1, we can calculate the intensity I2, I3, I4. So we can do the logarithm of that, and then we obtain, what do we obtain here? We obtain a set of 4 linear equations with 4 unknowns. If we set delta y equals to delta x, then we have a 2x2 inversion problem that links the mu k to ik. So we have 4 unknowns, 4 equations. That is something we can even imagine doing with paper and pencil. So we get from the intensities, we can get to the linear attenuation coefficients. Now let's say we have a n by m matrix. So if we have an n squared matrix, say 128 pixels that we want to have in our image, so it's 128 by 128 linear attenuation coefficients. And in principle, such a problem can also be inverted. Such a matrix can be inverted. The problem is this is very complex. It is computationally intensive, and also on top of that, the matrix inversion problem is unstable. On top of this, we have to consider nowadays that computed tomography was introduced in 1970. So we have to be a bit more simpler in the mathematical tools that are being used. We need a simple reconstruction algorithm.